you everybody for coming. Sorry for the AV difficulties. I guess that's what happens at the start of the week. Unfortunately, that means you'll miss out on all my animations, but under the circumstances, we'll make do with the PDF version. My name is Stuart Cheshire. I did my degree in computer science at Cambridge. I did my PhD at Stanford. While I was there, I was one of the few Mac users. Everybody else was running Linux. And I got tired of all the other Stanford computer science PhD students coming to use my computer to print because they couldn't figure out how to do it. I was quite vocal about the terrible state of ease of use for IP back then compared to Apple Talk, where you just pull down the Apple menu and click on the chooser, see a list of printers, pick one. I became co-chair of the IETF Zero Configuration Working Group. I served a term on the IAB. I wrote the O'Reilly book you see there, Zero Configuration Networking, and I am currently a distinguished engineer at Apple. So Apple Talk in the 80s was well known for its ease of use. And what we'd like with Zero Configuration IP is nobody ever has to type an IP address, not to configure a device to set it up, and not to connect to some service on some other device. And if you think about it today, nobody has to type MAC addresses. We have this protocol called ARP that maps from IP addresses to MAC addresses. We should do the same thing with IP addresses. Users should deal with names, and we should map those programmatically to the current IP address of that service. Why do you care? If you're making products, it lowers the support costs if people are not calling because they can't make it work. It saves you money if people are not returning the product because they can't make it work. It makes entirely new product categories possible, which would not be possible. There would not be a market for them if they were so difficult to use, nobody bought them. And perhaps last but still interesting, it makes products that are a pleasure to use instead of a pain. We still see applications that look like this, that ask users to type in the IP address of the thing they want to connect to. These are some pictures from when Apple introduced AirPrint. You tap on print and you see the available printers. Nobody types in an IP address. Apple uses zero configuration networking for things like AirPrint, AirPlay, HomeKit. You won't see anything in those UI where the user has to type in the IP address of what they're connecting to. This is especially critical for devices that have no screening keyboard. Think about Wi-Fi access points. The only way you can configure and manage a network device with no screening keyboard is over the network. So you have to have absolutely reliable networking, because if it can't be reached over the network, there is no way to reach it. 20 years ago, we had serial ports and you'd connect a VT100 terminal to it and manage it over the command line. And there are still some products like that. But more and more, we want to move to a world where we don't need a serial port as a crutch to make our networking work. The networking should be self-sufficient. So how do we realize this vision? There are three supporting technologies. The first one is you're not going to do much IP networking without an IP address. DHCP is great. If you don't have a DHCP server, you don't want the product to fail. So that's where self-assigned link local addressing comes in. This is really simple in v4 and in v6. You pick a random address within the designated range. You send an ARP or neighbor discovery request to see if it's already in use. And if it is, you pick a different one and try again. So that's great. We now know that all our devices will have an IP address, maybe randomly picked, maybe DHCP assigned. But if we don't know what the address is, that's only got us partway there. So we want to do naming. DNS is great. If you have DNS set up and you have the infrastructure to do that, then that's a great way of naming devices. Just like with link local addressing, where we want to fall back when DHCP is not available, we want to fall back when DNS is not available. And that is Multicast DNS, which adopts as much as possible the same naming syntax, the same record types, and as much as possible the same semantics, except it is done using multicast, where the querying client sends a multicast to all devices on the local link, and if any match that name, then they respond. You can name your devices with anything ending in .local, and the .local is what signifies to the underlying resolver infrastructure to look this up with multicast on the local link. So once this is in place, you can type printer.local into your web browser to access the printer's web UI to check the ink levels and things like that. Or for developers, it's super convenient to be able to log in with SSH without having to remember IP addresses. They can access their devices by name on the local network. So this is a step forward, but you still need to know what name to type. And if you type it wrong or don't know what to type, then it doesn't work and you don't get any helpful error message. So the third thing we need is discovery. And there are three basic operations in discovery that I call offer, enumerate, and use. Offering is the step where a device that has a listening socket, TCP, UDP, QUIC, SCTP, any other protocol, if it's listening for incoming requests, then it can advertise that on the network. Clients that are looking for that type of service can then browse or enumerate the instances on the network that can meet their needs. And then finally, having picked one, either the human user picking one or with machine-to-machine applications, some algorithm chooses the appropriate one, maybe just the first one it finds in some cases. Having made that choice, the third step is actually using it, which means finding the IP address, making a connection, and so on. Sometimes this happens once. Sometimes discovery is just used for onboarding a device onto the network. I'll give an example with the HomeKit products that do home automation. When you get them out the box, they're advertising a service type, which basically says, I'm an unconfigured device waiting to be set up. The client, in this case an iPhone, browses for that, finds those devices, communicates with them over the network using the setup protocol, and once that's done, they're now set up. They are no longer an unconfigured device. In other cases where you, for example, select your default printer, then you may do that selection once, but every time you hit Command P and print to that, you may do that multiple times per day. So this discovery stuff sounds nice. One of the things we want to keep in mind here is very constrained devices. I talked about HomeKit, building automation, IoT. A lot of these devices have limited resources. We've already decided we need DHCP and self-assigned addresses. We need DNS and multicast DNS for naming. If we can leverage that code that we have anyway to do discovery as well, then that saves us having a whole new body of code. So let's get a bit deeper into the three operations I talked about. The first step is offering. A device, a service running on a device, a piece of software, uses the discovery API to publish DNS records describing the service. And those three record types are PTR, SRV, and text. You might ask, what are those records? Well, when I show you the next steps, that will become apparent. So imagine you are trying to print on your iPhone using AirPrint, and you're looking for printers that support IPP. You send out that query on the network, and you get back, in this case, there are 4 different devices that are answered, each with different names, and the user can then take a look at that list and decide which one they want to use. This is the browsing or enumeration step. Once the user has picked one, we go to the next step, which is actually using it. So in this case, we look at the SRV record and the text record for that name that the user picked. The SRV record tells us the target host and the port on that host. The text record gives us a bunch of key value pairs that describe other attributes of the service. In this case, for example, it says the page description language that this printer supports is PostScript. Also, by the magic of DNS additional records, even though the client didn't ask for the address record of the printer, the responding device knows that he'll probably need that information. So for the target host referenced in the SRV record, it has an additional record giving the address of that to save the client doing another round trip to look it up. Notice the port number in the SRV record. This is incredibly helpful. This frees us from having to use fixed, well-known ports. If you want to run multiple instances of a service type on the same device, they can't all have the same port. And this leads to very complicated workarounds. HTTP has the host header, which lets a server act as multiple virtual servers, but it's kind of awkward. IPP has similar demultiplexing, but every application has to invent this demultiplexing. If you just run each instance on its own port, it's much simpler, and that wasn't possible with well-known hard-coded ports. But service discovery frees you from that restriction. So going back to these results, let's take a little bit of a closer look at that name on the left. It is a structured name made up of 3 parts. The first part is the user-friendly, visible name of that instance of the service. It is arbitrary UTF-8 text. It can contain uppercase, lowercase, spaces, punctuation, anything you can represent in UTF-8. Typically, users don't have to type this name when they connect to a service. Typically, they're using a graphical user interface and they click or tap on it. So keeping it short and easy to type is less important than have it be descriptive. When you set up the device, you name it however you want, and having done that naming, then other clients just select it by tapping. The second part of the name is the service type, which tells us what it does, and the final part is the domain. So let's look at those 3 in a bit closer detail. Starting with the instance name. There are 2 kinds of names at play here. There are the host names and the service names. Host names are what we're used to thinking about with DNS. They're often typed on the command line with things like SSH commands in terminal windows, and it's definitely convenient to have those to be short and memorable and easy to type. And it's good if they don't have spaces, because shells get confused with spaces in arguments. Service names, on the other hand, should be as rich and varied as file names. And we used to have DOS 8.3 file names, all capitals, but we've moved on from that. And the same is true with service names. Having rich text naming is something we should expect in today's world. This is a point where I'll make a little digression. Something we see a lot of vendors do is they feel the need to make the names unique in the factory by stuffing the MAC address into the name. And it's a mystery to me why people sometimes think this is a useful thing to do. Because Multicast DNS has name conflict detection and automatic renaming. So let's consider 3 different scenarios. One is the average home user has 1 printer. They don't need a 12-character MAC address. If the printer is called HP LaserJet, then that's their printer. Now imagine a small dentist office where they have 2 printers. They have one and it works fine, and later they decide to get a new one. The second one they add will detect the name conflict and call itself HP LaserJet 2. Now, most people in the dentist office, without even thinking about it, will very instinctively remember that's the old printer I've been using for years, and the new one is printer 2. No confusion. 2 different MAC addresses, much harder to remember than the new one is number 2. Third scenario is imagine you have 10 printers. Well, at this point, memorizing 10 MAC addresses is no use to anybody. Numbering them from 1 to 10 is at least a little bit better. In reality, when you get up to these numbers, what makes sense is for the administrator, the person buying and installing this, should go into the web UI of the device and give it some kind of more meaningful name. But in none of these cases is MAC addresses any use to the end user trying to tell what thing they've discovered. So let's move on to the second part, the service type. This seems very simple, but there are some subtleties here. This is not displayed to the user. This is something only programmers see. So there is no value in rich text here. They're limited to 15 characters, letters, digits, and hyphens, just like traditional host names. That is a big enough space that they're effectively unlimited. They're allocated first come, first served, and there's no risk of running out. On the other hand, the identifier space is short enough that it's not wasteful in packets, particularly for these IoT type applications I'm talking about. You want to be mindful of wasting bytes in packets. The second half of the label is the protocol type string. This was inherited from the definition of DNS SRV records. In retrospect, looking back, it probably isn't necessary and it causes confusion, but it's a legacy from what we adopted. And the rule is if the protocol runs over TCP, it ends in _TCP, and everything else is _UDP. And that would include things that actually don't use UDP, but they're pretty rare. Things like Quick actually run over UDP. So that's why the world is divided into there is TCP and there is UDP and nothing else. Now, the semantics of the service type string are really important because they encode two things. They encode what the service does and how it does it. What it does is a user meaningful concept, like, say, printing. That is something somebody understands. But there are many ways of printing. There's IPP, there's the old LPR protocol. There is a collection of proprietary printing mechanisms that traditionally use port 9100, variously called AppSocket or JetDirect. If you discover an IPP printer, but your client doesn't support IPP, that's no use to you. So it's not sufficient just to have the logical service that the user wants. You actually have to have a compatible implementation. And this is important the other way around as well. I can give an example. The music streaming protocol built into iTunes is actually just HTTP GET. You can share your music library on your home network, and other clients just do HTTP GETs to fetch it. So at some level, the protocol is HTTP, but semantically, this is not something you would use a web browser to view. There is no HTML formatted text for a human to look at. So the service type for that is not HTTP. It's a different string. It's DAAP, Digital Audio Access Protocol. Even though Wireshark would look at it and decode it and perfectly well say this is HTTP, semantically it is a repurposing of HTTP. So the service type encodes both what the user perceives they're doing and the protocol that's being used to do it. Here are some examples. IPP is printing, SSH is remote login, remote frame buffer is VNC screen sharing. You can see all of these in use. If you have Macs here in the terminal window, press Command-Shift-K, it will bring up a browser showing you all your fellow IETFers who've got SSH turned on their machines. It's important that these service types don't collide. So IANA maintains a free registry like many of the other registries they maintain, and it is first come, first served within reason, unless there's an abusive number of excessive registrations. There are no restrictions on getting a service type assigned, and you just fill in the form and you get one, and it's yours in perpetuity. It doesn't have to be renewed every year like a domain name. Before shipping your product, do register your service types, because it would be awkward if somebody else used the same name and then you have inadvertent conflicts on the network. Now let's get to the third part of this name, the .local. Well, .local tells the underlying system, look this up with Multicast. But if the name is not .local, then that means use the standard DNS that we all know and love. Is there a question there? Okay. Am I not close enough? Is that? Okay, thanks. Like that? Is that not towards my mouth? Okay. Okay, we'll see how that works. I'll just try to talk louder. So when you're not using .local, when you're using some other domain, then normal DNS that we know and love comes into play. Services can publish their information using DNS update, and clients discover it using DNS queries. And DNS is the largest distributed global database that I think the world has ever seen, so it is incredibly scalable. We use it for storing host names. We can use that same distributed database for storing service information. We've been doing this for many years at the IETF, and you may have used this without even thinking about it. If you print out your boarding pass or print out an internet draft to read, sitting here, you can find the printer in the terminal room. And you're not in the terminal room. You're not on the same local link as the terminal room, but it still works. And if it didn't work, people would grumble and curse, stupid multicast DNS doesn't work across links. But when it does work, nobody pauses to think, what just happened there? They hit print, they get their boarding pass, and they're happy. So I want to do a bit of a walkthrough to demystify what's really going on here. It starts with DHCP, and you can walk through these commands, and you'll see this happening here at the IETF meeting network. These commands are done on my Mac. When we look at the information we got from the DHCP server, we look at option 15. Here it's displayed as hex, but if we decode that, it tells us that the domain that the DHCP server is reporting for this network is meeting.ietf.org. Okay, that's a good start. So now we look up this special query with the prefix lb.dnssd prepended onto meeting.ietf.org, and we do a PDR query. And what that is asking of the DNS infrastructure, specifically asking the people who run the authoritative server for meeting.ietf.org, is, do you have any service discovery information? And if so, where should I look? And here we get an answer. And it's a sort of self-referential answer. It says, look in meeting.ietf.org, but because it's a pointer, it could direct you to services.ietf.org or wherever. In this case, it's simply a self-referential answer pointing to itself. So now we know where to look. We can start looking up services. And one of the questions that people often ask me, or one of the assumptions that I hear people have, is that you have to be quotes on the IETF network. And that's sort of a loosely defined term. What does it mean to be on the IETF network? What is the IETF network? DNS is global. So here's an example doing the exact same query sent to Google's Quad 8 servers, and it gives the same answer. The answers that you get from DNS for public names don't depend on where you are. Now, VPN and internal DNS at companies does muddy the waters a little bit here, but broadly speaking, for public names, you can look them up on any resolver in the world that'll consult the same authoritative service and get the same answer. So now we know where to look. This is what happens when you go into System Preferences on a Mac and click the plus button to add a new printer. It does a PTR query on the network, and here at the IETF, we find one printer called term-printer. They could have named that a bit nicer with capital letters and things, but that's what they chose to do. So when you do this on your Mac and click plus, this is how at the IETF meeting you'll see that printer show up. When you actually want to print, this is the use step. You then look at the SRV record for that printer, and you find that it is implementing that printing protocol on port 9100, and there's the IPv6 address, and you can print. If we do the same thing on iOS, it does the query and it prints. Notice here that iOS is using IPP, so it's a different service type, and the port number is different. So same hardware, different protocol, different port, same result, toner on paper. Now, those of you who are watching closely would have noticed something there. In the query that the iPhone did, it has this prefix universal, which is a subtype of IPP. Subtypes are a little used feature of service discovery, but I want to mention them here for completeness because they can be useful if you need that. Subtypes are a way of narrowing the scope of what you find. So in the case here, there is no way for vendors to install custom drivers on an iPhone. iPhones only support driverless printing using the IPP protocol, but specifically, the printer has to support a format called Universal Raster format. And the printer can optionally support many other formats as well, but the mandatory to implement format is it must support URF, because that way you know that your device may not be able to send PostScript or PDF or JPEG to this printer, but in the worst case, it can send a raster image and the printer will print it. So the _universal subtype of IPP is the subset of IPP printers that also implement URF. So if you have a use case where you want to narrow your search to a subset of a particular set of devices that have a service type, subtypes let you do that. So now let's get on to how you can use this. It is included, I'm sure everybody knows, in macOS and iOS and has been for more than 15 years. Most Linux distributions include the Avahi LGPL implementation. Android started including it in 2012, and Windows 10 in 2015 added their own native DNS service discovery APIs. The best way to get started, if you just want to play with this and prototype, is to use the DNSSD command line tool, which is installed on Macs. If you get the MDNS Responder project for Linux or POSIX, you just type make install, and it will install the daemon and the same command line tool. If you have Bonjour for Windows installed, then the same tool is there. This is not intended for you to embed it in scripts and use it in production software, but as a quick and easy way to kick the tires and see whether this works for you. It's a very low overhead way of trying things out. And if any of you are interested in seeing this in more detail afterwards, we can sit down and do some experiments together. It supports the 3 operations I talked about: offer, enumerate, and use. The -R option registers your service with the underlying daemon. You tell it the name, type, domain, and port you're listening on, and then that is published on the network, either with Multicast DNS, if it's local, or if it's some other domain with a DNS update. When a client wants to find those, it does a browse operation, and you'll see the parameters are very similar, except you miss out the name. You say the type you're looking for and the domain you care about, and the result you get back is the list of names. And then finally, the lookup or resolve step that you do prior to connecting, you tell it name, type, and domain because that's what you learn from the browse step. What you get back is the target host and port. How you select local and wide area. This is one of the benefits of having it designed on DNS this way, is it's not a different API. You use the same API, you get the same semantics, you get the same behavior. It just depends on whether the domain is local or something else. In terms of API usage, if you're writing an application, we recommend that you don't specify a domain, just pass null or empty string, and that lets the underlying system apply the user's defaults. Most of the time, that will just be local, but as you saw at the IETF meeting, where you get hints from the network that in addition to local, there may be other domains that have interesting things for you to find. If you pass null, the system will do the union of all those discoveries. If the printing system passed local as its domain parameter, it would only ever find local things. By leaving that unspecified, it allows the system defaults to come into effect. So here are some examples, which for those of you who have Macs or Windows with Bonjour for Windows installed, you can try these on different terminal windows on one machine or on different machines. That example shows advertising a service called test of service type _test, browsing to find those instances, and finally looking up the connection information. So that's how you prototype with the command line tool. For programming, you'll want to use C APIs or Java or Python or whatever language you're using. I'm going to talk here about the C APIs that are defined in DNS_SD.h. That is what has been used since we started doing this on macOS and iOS. If you install mdnsd on Linux, it's the same API. If you install Avahi, Avahi has its own API, but it also has a compatibility layer that supports the same APIs. And Bonjour for Windows has the same API. Android additionally has its own Java-based APIs that were introduced in Jelly Bean. So there's a link there which you can get in the PDF to find the documentation for that. Windows, similarly, when they added their own implementation, they had a slightly different API, and the documentation is there. But I'm going to talk about the C APIs that I'm most familiar with here. This is how you register a service. There are a bunch of parameters. The first parameter is actually an out parameter. That is the result of doing this call. That is a service discovery reference. There are some flags which are optional. Typically, those are 0. You can specify an interface index if you want to constrain it to one physical interface. Again, normally you just pass 0. You advertise on all interfaces. You specify the name, type, domain. If you're advertising a service on a different host, then you can do that. That's for proxies. Typically, that would be null. You specify the port you're listening on. If you have any key value pairs, then you pass a text record. And all of these routines take a callback function, which gives you asynchronous notifications of events. Now, if you compare this function with the browse function, you'll see a bunch of the parameters are the same, but with some missed out. You don't specify the name because you don't know the name that you're looking for. You don't specify host and port, but the other parameters take the same form. And likewise for resolve, it's extremely similar. You now specify the name you're looking for, but things like the port and the text record are the results you get when your callback is invoked. So one thing you may have noticed here is all of these calls are asynchronous. And that's because networking is at its heart asynchronous. If you browse the network for services and the Ethernet cable is not connected or the Wi-Fi is not associated, you're not going to find anything. And it's not helpful for the call to fail and the application has to then have a retry loop, maybe wait for the configuration to change. It's much easier to have the API just handle that. So when you start a call going, that call will run until you change your mind and tell it to stop. And any changes in the environment or configuration that happen during that time are just handled automatically. The way that asynchrony is handled, because over the years there have been many different models of asynchrony, threads used to be in fashion, but it can be difficult to get that right with race conditions. Event loops are now more popular. There are things like Apple has CF run loop, there is libdispatch, there's select and poll and k-event. There are many different ways to have an event-driven system. The way you integrate this into whatever system you're using is you extract the underlying file descriptor from this SD reference object, and then you add that file descriptor to whatever your event handling mechanism is. And then when you get notified that there is data readable on that file descriptor, you call DNS service process result, it will parse that data and call your callback function as appropriate. If you get the open source MDNS responder code that I pointed you to earlier, then in there is the source code for the DNSSD command, and that is a great source to crib little code snippets for the thing that you want to do. The main function of that is basically a big switch statement for each of the operations, and you just pick the case in that switch statement that applies to what you're doing, and that will show you how to register, browse, or resolve. The asynchrony is really important for a good user experience, and you may notice that you will not find a refresh button anywhere in any of the network browsing API, UI that Apple ships, and that's because it simply calls the API, The browse call runs asynchronously. As things come and go, the results are updated. If you do a browse with no networking, you find nothing. You associate with Wi-Fi, you find some results. You turn Wi-Fi off, those results go away again. If you roam to a different access point, then the old results go away and new results are discovered. This continuous change monitoring will happen indefinitely for as long as you leave that browse running, for hours, days, weeks, in principle. If you're writing an application, please don't browse for weeks. That's really hard on the network, but if you did, it would work. The asynchronous results are worth mentioning in a bit more detail. They also give us something really useful for free, and that is event notification. There are many systems that, in addition to everything else, they have a completely separate publish-subscribe mechanism for events. Well, we don't need that, because having the ability to do continuous operations that are updated as the environment changes means that those give us notifications as well. So here is an example. You have some service on the network. It registers its service to publish it on the network. As data about that service changes, let's say the ink level in the printer or the paper in the paper tray, it can call DNS service update record to update its text record with new data. And a client that wants to be informed of those changes as they happen uses DNS service query record, which is not a one-shot query, it's an ongoing monitoring operation. It will continue giving you callbacks until you cancel it. And that would, for example, allow a client to monitor the ink level of the printer and see it going down over time without having to continuously poll every 5 minutes or every 5 seconds to find out the data. So if you need something like this, this is an incredibly simple and powerful mechanism. This works for both local and remote services. For local services, when the publisher updates the record, a multicast announcement is sent out to all the peers on the local network, and listening clients get a callback notifying them. The remote case is more interesting, and this was more work to build. The publisher sends a DNS update to the registry to update its information, and clients that are interested use DNS push notifications to register that interest. And when the data is updated, the registry then automatically informs any interested clients. So that lets remote clients across the building or across the world get live updates to information without having to continuously poll to find it. So some tips if you're building browsing UI. You don't need a refresh button. We really request that you don't leave browse operations running indefinitely. There is a temptation when your application launches to start a browse in the background and keep it running so that you keep a data structure in memory hot just in case the user wants it. That is very expensive on the network, particularly Wi-Fi. Multicast on Wi-Fi is very inefficient and very slow and consumes a lot of airtime. Unicast Wi-Fi goes at tens, hundreds, in theory, up to 1.3 gigabits per second and higher now with Wi-Fi 6. Multicast is down at the single digit 1 to 6 megabits per second. So a single multicast takes as much airtime as 100 unicasts. It is very, very expensive. So casually browsing in the background can consume a lot of shared network resources. So the better way to do it is if the user brings up a browsing UI, for instance, they tap the AirPrint button, that's the time to start browsing, show the results. You will see that it is already fast enough that the results appear within less than a second. So there's no real incentive to keep a list in memory in advance. And then when the user dismisses the UI, stop the browse operation. Another tip, as a general rule, users get frustrated when menus change underneath the mouse as they're trying to select something, whereas windows that change are still can be confusing, but they're less objectionable. So we really recommend that you bring up a window showing browse results rather than displaying it in a menu that then shuffles around underneath the user's mouse. And the final step is that there is a very deliberate, conscious reason that we have the three basic operations: use, enumerate, offer, use, enumerate. They're separated so that they can be done separately. The enumerate step will find everything on the network and show the user the names. At that point, you don't need to look at the IP addresses because the user hasn't chosen which one to connect to yet. Or in the case of software, the software client hasn't chosen which one to connect to. So it's only when you actually want to connect that you then look up the address for that particular service. In many cases, you browse the network to find something. So the familiar example is setting up a printer. You go into the printer preferences, you click plus, you add a printer. Some tips here. We have seen people make this mistake. When you find the printer, if you save the IP address, well, with DHCP, that might be a different address tomorrow. If you save the address and port, well, with dynamic ports, the port number might be different tomorrow. So the right way to think about this is late binding. Store the name type domain tuple of the service that was selected, and then at time of use, you look that up to the current address and port that's in use at that moment in time. So here's an example of information you can find. And that first column on the left is what you find by browsing the network. You get a list of names, and that is a small amount. It is 7 bits of information. And if you look at one row on that chart, that is the detailed information about a particular service. But if you browse the network and resolve everything you find, you're finding all the information about all the services. And that is a very expensive operation, especially, as I said, on a shared network like Wi-Fi, where you're consuming everybody else's shared resources to look up this information that you probably won't need. So, final advice here. Only resolve when you actually need the information, because IP addresses change and you want to get the latest information at time of use. Another thing to note is when you resolve, modern devices may have multiple addresses. They may have v4 and v6. They may have link local and larger scope addresses. And if you just take the first one and that doesn't work and then you fail, that's not a good user experience. We have known this for a few years now. We highly recommend you follow the guidance for happy eyeballs. Now, you can implement this yourself, which is a bunch of work, or you can use an API that does it for you. And here is an example from Apple's suite of APIs using Network Connection, which is our current recommended API suite. You simply tell it the service name type and domain you want to connect to, and it will handle resolving, getting the asynchronous results, sorting the candidates into a logical order, trying each address in turn. If it doesn't get an acknowledgement after some number of milliseconds, moving on to start a second parallel connection attempt to the next candidate, and so on. So we really recommend you use APIs that implement happy eyeballs. It gives a much better user experience. So this is the point where I often have people say, this doesn't sound so hard. We invent our own broadcast protocol. We don't need to use this. And I understand why it seems that way, because it doesn't seem like it's very hard. You broadcast some packets, you listen, you answer. And when we started this, it didn't seem that hard. Apple Talk did name binding protocol. We thought we'll do the same thing. A year or two of work, this will be finished. And what we found is to build a really, really good service discovery protocol, there are lots of things you have to take into account. One obvious one is that Wi-Fi is very lossy, so you have to have retransmission. Okay, no big deal. Everybody knows retransmission and exponential backoff. There are questions about how you tune and tailor that to give the right performance. Wi-Fi multicast is also very slow. So we have a lot of techniques to maximize the efficiency of how we use the network. One is if you do a multicast query for IPP printers and I see it, then because all the responses are sent by multicast and I see those responses and I opportunistically cache them, if you do a query, I will see the same answers you do. So if later the user on this iPhone presses the AirPrint button, we don't need to do another browse because I got to piggyback on the browse that you did and I already have the results. So duplicate query suppression prevents multiple devices on the network from doing the same query. To minimize network traffic, we have long cache lifetimes. So once you've seen something, it stays in the cache for a long time. Now I'll come back to how we manage that. Because of retransmission, if you do it naively, every time you retransmit, you get the same set of devices answering. So you say, I'm looking for IPP printers, and you get 10 replies. Well, there might be packet loss. Maybe there's one that you missed. So you retransmit, and you get the same 10 replies. And you retransmit, and you get the same 10 replies. This is very wasteful. So the queries include known answer lists, which in effect say, this is what I'm asking for. This is what I already know. So if you're in the list, you can keep quiet. Is there anybody else that I missed? I don't know any other discovery protocol that implements known answer suppression. There's also duplicate answer suppression, which comes into play when you have proxies. Now, for various fault tolerance and reliability reasons and other reasons I'll come to later, you can have proxies on the network that answer on behalf of other devices, and you can have multiple proxies, but you don't want them all answering. So the answers are delayed by a random interval, and the answering devices also listen for answers. So if they were planning to answer, but then they see the same answer come from somebody else, they can suppress their own answer. So this is another one of the techniques that's used to minimize the amount of multicast traffic. Now, I talked about the exponential backoff for queries. Again, if you do this naively, you get a very poor user experience because you query again, you wait a bit longer, you query again, you wait even longer. Pretty soon, it settles down to a quiescent query rate of no more than 1 query per hour. Now, if a new service comes on the network, waiting up to an hour to know about it is not a good user experience. So hand in hand with the queries and exponential backoff, when a new service joins the network, and that includes both starting up a service or starting up a service and then connecting the cable, or then associating to Wi-Fi, and those link change events are detected. When the new connectivity happens, then the service sends gratuitous announcements so that if there are clients who have been listening for a long time, they immediately get notified of the new service. So that gives you very rapid discovery without rapid polling. Another aspect is we manage name uniqueness, which is why you don't need to have names unique from the factory. You don't need MAC addresses. You can have simple names, and if the name is detected already in use, then the API will rename your service with a 2 at the end, or if you prefer, it will call your callback function and give your code the opportunity to pick a new name. So I talked about the long cache lifetimes. This is good for efficiency, but it's not good when things go away. Now, if a service shuts down cleanly, it sends goodbye packets on the network. But suppose the power fails, then it goes away without saying it's going away, and that data will remain in caches. Now, as long as the user doesn't try to use the service, that's kind of benign. It's sort of like if the tree falls in a forest and nobody's there, do they care? But at the moment the user actually tries to use that service and it doesn't work, that's when they get frustrated. And if they get an error saying can't connect and they go back to the browser and it's still there, then they get really frustrated. So we do this lazy cache cleanup where if there's a connection failure, even though the cache record might have 45 minutes to go, we decide we don't trust that, and we do a couple of queries. And if it doesn't answer, we remove it prematurely from the cache. So by the time the user goes back to the browse UI, that thing has disappeared. And they at least now have a mental model of what happened. They think, oh, somebody just turned it off. And they walk down the hall and find the printer's turned off. Well, that's not necessarily true. Maybe it wasn't just turned off. Maybe it was turned off half an hour ago. But it doesn't matter, because the user at least has a mental model about what happened and what to do about it that isn't frustrating. A refinement beyond that is that if you try to print and fail and remove the printer from your list because it's turned off, I passively eavesdrop on that transaction. I see you querying. I see no response coming back. I update my cache as well. So one user discovering that something is not visible serves to inform all the devices on the network to update their caches. So this is how we get rapid addition and removal of entries without a high burden of polling on the network. And then a final thing that is really important if you want a good user experience is mobility. When you put a device to sleep, it sends goodbye messages saying its services are no longer available, with an asterisk. I'll come back to that. And when you wake it up, it re-announces. When you change your connectivity, then it reissues queries, it re-announces services. And that includes even subtle cases where you roam to a different access point. You may be on the same Wi-Fi network name with the same IP address and the same default router address, but if you switch access points, the multicast domain you're in may be different with a different set of services. Handling all of these things in your own code is really subtle, which is why you benefit if you use a very mature implementation that has done all these things. I said the little asterisk about going to sleep. One of the things that we support is a sleep proxy. So you can have a device, if it supports Wake on LAN, when it goes to sleep, it notifies a sleep proxy of what its services are, what its name is, what port it's listening on, and that sleep proxy can then act on its behalf and wake it up on demand. That way you can have devices that offer services on the network that are available even when they're asleep to save power. And finally, using these existing APIs gives you remote discovery like we use at the IETF. It also allows discovery via this thing called the discovery proxy, which I'll mention. So here's the example I was talking about with a sleep proxy. You may have a USB printer plugged in with printer sharing, but the Mac's asleep. The sleep proxy on the network answers on its behalf and wakes it up when the client wants to talk to it. A discovery proxy is what lets you do discovery of legacy multicast DNS devices from multiple hops away. Now, if this phone on the left sends multicast queries on the local link, it's not going to find the printer because it's not on the same link. This is similar to the situation here at the IETF when you're not in the terminal room. Now, at the IETF, we have expert volunteers who run the network and the DNS, and they manually put the records in. But for normal users, we want to automate this. And that's what the discovery proxy does. It acts like an authoritative DNS server, except when the client sends it a query, instead of consulting a zone file that was typed in by hand by an administrator, it uses multicast DNS on the local link to discover what's available, and then uses that to generate the unicast answer back to the client. So using that, we wouldn't need the NOC volunteers at the IETF to manually manage these records. So to wrap up, there are some links in the PDF that you can download. If you're making a hardware device, then I strongly recommend you do link local addressing. Here are the RFCs that tell you how to do that for v4 and v6. Here are the RFCs, several years old at this point, for the basic service discovery stuff that I've been talking about, and the IANA procedures for registering service types. There is a bunch of new work going on. The wide area unicast registration builds on DNS dynamic update with an addition that Ted Levin has been working on called Service Registration Protocol, which basically builds on DNS update by using SIG0 public keys to give a really low overhead, simple, first come, first served, but secure naming system, where any device can claim a name, but having claimed it and installed the key, it gives you some protection against some other device coming along later and masquerading as that. DNS stateful operations is the foundation for the query side features we've been building, and that includes push notifications for asynchronous change delivery and the discovery proxy, which lets you automate this export of local multicast DNS information to the wider space. And if this seems like a mountain of information, you're right, it is. The final link there is the roadmap document, which gives you an overview of how all these pieces fit together. You can get the source code from the IETF Hackathon GitHub page. That includes the source code for the command line tool. There is a great tool called Discovery, which is a graphical version, which is a free download from the Mac App Store. And then finally, if you're building a hardware product, you can get the Apple Bonjour conformance test for free and run that to validate your design, because that is designed to catch many of the common implementation mistakes we've seen over the years. So the call to action here is, if you're writing a piece of software that currently expects the user to type in a name or an IP address, you can carry on doing that, but add a button for browsing as well, so the user can pick from what's available. If you're building a hardware product, do link local addressing, because that's what gives your product bulletproof reliability, even when things like DHCP are not available, and use the conformance test as a verification. So that is the end. Thank you for listening, and we have a minute or two for questions if we have any. Oh, and I do remember to fill in the survey. It helps the Edu team maintain the quality of the tutorials we have at IETF.
Sorry, two questions, yeah. The first one actually is, if I have 10 printers, right, print at the same time, they'll rename it, they'll name it from printer 1 to printer 10.
Yes. But
how physically you can identify which printer is which printer? Printer, you can print a test page to identify which physically a printer. But for IoT devices, how can you do that? It's only the way is MAC address, right? So typically, that's the first question, right? The second question actually is, if printer number 5, I need to replace it, what is the procedure?
Okay, so there are two questions there, which is, how do you identify devices and how do you replace devices? Excellent questions. The way you identify devices is somewhat application specific. There are a couple of ways this is done in practice. One is, if you buy a device and then buy another one, the next one is number 2. And then if a week later you buy another one, that's number 3. So simply by virtue of the fact that you had 2 devices on the network and you add a third one, and now you have a device number 3 on the network, well, the one you just added is device number 3. So in many cases, that is not confusing. If you are getting 10 things or 100 things out of a box all at the same time and connecting them, then you're absolutely right. In that case, the service discovery protocol is not going to tell you which is which. In the case of IoT, there is typically, I know with the HomeKit stuff is what I'm familiar with, but there are many IoT, home automation, building automation protocols. There is normally a command to have a device identify itself by blinking a status light. So in your list of things, if you see number 3 and you click identify, you see which one has the light blinking. I still think that saying device number 3 and seeing the light is blinking and maybe getting a post-it note and putting a 3 on it is easier than putting a 12-digit MAC address on it and then having to somehow remember all those MAC addresses in your head. And remember, this is often only the bootstrap step. This is the out-of-the-box configuration. What you typically do with a bunch of IoT devices is you give them names, like bedroom light switch, downstairs hallway. You don't, no user wants to see a list of MAC addresses in their home automation application. They want to see descriptive names. So that is a case of the out-of-the-box configuration step. And then to answer your second question, what happens when you replace it? That is an excellent example. Say printer number 5 breaks, and you go out and you replace it with an identical printer because you love the printer. It was great. The employees in your company love it. We just want another one the same. You buy one exactly the same. You give it the same name through its web UI or whatever configuration tool. You put it on the network, and then because the names are the primary identifiers, they identify the logical service on the network. Then the employees come to work next day and they print on printer number 5, and printer number 5 answers and the paper comes out. And the fact that the atoms have been replaced with new atoms doesn't change the fact that the service it's providing, which is printing paper in the copy room on the 3rd floor, that service is the same, even though the physical thing has changed. And being able to give a new thing the old name so it takes over that role on the network is a really useful capability. Okay, I think we have time for one more question because we did start late and we're running over, but one more, I think.
This isn't even a question, it's mostly a comment. As Stuart said, service name registration is easy. Don't be intimidated by the IANA form that you have to fill out, but please be sure that if all you need is a service name, just ask for the service name. Don't also ask for the port. You'll save yourself a lot of hassle.
Yes, I echo that. The form asks lots of questions. Ports are in short supply. If you ask for a well-known port, expect a grilling about why you need it. If you leave the port number blank and say, I want a service type, you'll get a big cheers from IANA saying, thank you for not wasting a port number, and you'll get a very rapid confirmation of your allocation. Okay, well, thank you all for coming. Please do remember to fill out that survey.
You're gonna.
I'm
Send me the picture.